So our next speaker in this morning's session is Dr. Danila Barskiy. He is now at Johannes Gutenberg Universität at Mainz. The title of his presentation today will be Zero Field NMR Detection of Molecules Hyperpolarized by SABRE-relay. So we're very much looking forward to this presentation. The floor is yours, Danila. Please go ahead. Thank you.
Thank you, Ed. I'll try to be quick so we can join at least some short break maybe. But indeed, first of all, I wanted to thank organizers for providing me with the opportunity to present our recent results. And I also immediately want to thank our funding, which is Sofia Kovalevskaya Award from the Alexander von Humboldt Foundation, which actually allowed me to move to Germany roughly half a year ago, a little more. And we're going to present results related to zero field NMR combined with the hyperpolarization technique SABRE-relay. So first of all, a few words, why zero field? Why is it interesting? I was always excited by tools and techniques of NMR and MRI. However, we all know that they require high magnetic fields, and therefore, usually they're not very portable. For the same reason, due to very high magnetic fields, these are relatively dangerous techniques in the sense that accidents happen and people get injured. So both of these problems could be eliminated somehow if we were able to remove magnetic field to begin with. And yesterday, John Blanchard gave a beautiful presentation. I will quickly go through introduction of zero field NMR here for consistency. So in conventional NMR, your signal is proportional to the change of the magnetic field flux. Therefore, your signal will be proportional to the square of the magnetic field. Indeed, if you rely on thermal polarization, your polarization is proportional to the field. And as a derivative from the precession magnetization, due to Larmor precession, you have a frequency, which is also proportional to the magnetic field. So therefore, now it's clear why conventional NMR, or we want to go higher and higher in magnetic fields. We will increase both our signal and our detection sensitivity. So, however, we are here at this beautiful conference, parahydrogen, hyperpolarization, and there are many members from other techniques such as DNP, KIDNAP, and so on. And we don't have to talk too much what hyperpolarization can offer. Therefore, I can say, maybe it's not complete, but we already know how to fix the problem of high signal, so to speak. So what's left over, how can we detect signals from NMR, from nuclear spins, completely without magnetic fields, or better to say, without using large magnetic fields? So it turns out it's possible. And this is a very oversimplified picture how it works. In high field NMR, we use coils, which are volume sensors, right? But in zero field NMR, we use vapor cells, which are surface sensors. And I'm meeting all the complexity of the photo detection schemes. But the main principle is very simple here. Here you can actually detect signal itself, the field itself, by bringing your sample, which has magnetization evolving due to nuclear spin interaction, bringing it close to your sensor, vapor cell, and measuring signal with a photodetector. And this was beautifully pioneered. This research was pioneered by Professors Alexander Pines and Dmitry Butker from Berkeley. And this is a very beautiful paper by Thomas Theis, who is also an organizer of this conference. So indeed, by combining these techniques, you can completely avoid, so to speak, magnetic fields and do NMR without magnets. You can use parahydrogen as a source of your polarization and optical magnetometers, that's how this technique is called, for signal detection. I'm very happy as a chemist that now you don't have to actually yourself, not always, you don't have to build your own optical table and systems. You can just buy these beautiful devices called OPM, so optically pumped magnetometers. More and more companies are joining the market, but this one is currently the leader, is a Q-spin, and everything is located inside. So inside you have a small vapor cells, a laser system, which allows you to measure signals very well at the tip, at the surface of the sensor. And the main driver of this technology is magnetoencephalography, so the ability to measure signals from your brain, magnetic signals due to neural activity. However, as it was shown yesterday by John, it is also possible to use Q-spin devices and OPMs, commercially available devices for measuring your hyperpolarized chemical signals. And relying on this first work showed by John, Dima, and colleagues in Berkeley, we assembled our own device before moving to Mainz with a visiting student, Piotr Put, who from the group of Szymon Pustelny from Poland. And indeed, I was excited to see that the signals are indeed very, very good from these commercial sensors. Therefore, you know, and another advantage of the sensors is that you can actually put them on a portable card, and you have basically, you will not have problems with shaking and everything, which otherwise would be problems if you were moving the whole optical table with all your optical equipment. So it's definitely useful, and you can measure signals from important biomolecules, such as, for example, glycine or fumarate or glucose. But these measurements have been done with thermal polarization. And it's beautiful, in my opinion, that with portable sensors, which you can basically build, and then you can construct your own portable NMR spectrometer, you can actually achieve chemical information with the chemical specificity. So, however, it should be pointed out that in order to achieve this spectrum with thermal polarization, you need hundreds of averages and very large labeling, so basically fully labeled materials, as well as large concentrations. So obviously, in order to go towards some useful applications, you more likely will need hyperpolarization. And before moving forward, we will need, for the purpose of this presentation, to understand at least the very basic structure of chemical of J spectra. That's what we detect in zero field NMR. And we're going to focus today on the molecule methanol, C13 labeled methanol, in which OH group is usually undergoing exchange with other molecules. We can undergo exchange with other molecules in solution. But the main chemical motif, which will give you J spectrum in zero field, is XA3 motif. And you will see, you can calculate it very easily. You should see two transitions at J and 2J, corresponding to the J coupling between carbon and hydrogen, which is about 140 hertz in this system. So now I switch gears to this method, SABRE-relay, which, if I'm not mistaken, have not yet been covered on this conference, But the main point of SABRE-relay is an extension of conventional Saber. So instead of relying always on binding your substrate to be polarized with the iridium complex, you can actually rely on chemical exchange and use a first polarizable substrate which can bind to the complex and then transfer chemically hydrogens to another molecules. And obviously, chemistry, we know chemistry, NH3, for example, amino groups can exchange their protons very efficiently and effectively with alcohols, acid, amides, phosphates, as well as they can bind to Saber catalysts. And this research and technique and tool was pioneered by the group of Professor Duckett, and they show multiple beautiful examples of what type of systems can you polarize. You can polarize glucose, you can polarize alcohols, different types of nuclei. And we wanted to see, is it possible to use SABRE-relay to hyperpolarize methanol and then detect it at zero field NMR? So the challenge here, in principle, we know that methanol should be polarizable by SABRE-relay. And we also know that methanol should give zero field J spectrum. However, chemical exchange can have detrimental effects on zero field NMR spectra. Therefore, it wasn't completely clear, is it possible at all or not? And this work is performed by my student, Eric van Dijk, who is also having a presentation at the poster session tomorrow. So I invite you to join his poster. And there he will explain in more details, the details of his basically research. The main point before doing the zero field experiments, we wanted to optimize chemical composition of the sample and obtain largest hydrogen polarization on methanol. We used a very simple sample. It's not the most optimal, even given the literature data, but it was something which we could already find in a lab. As an amine, as a carrier amine, we used benzylamine, and as a substrate, we used methanol. And you can see that Eric did a lot of experiments with different concentrations of the iridium catalysts with different proportions of methanol and benzylamine, and it was found, and it confirmed results from the group of Duckett, that the largest molar polarization of methanol is observed when methanol and benzylamine are present in equal concentrations. So what is molar polarization? Molar polarization is a product of your polarization and concentration. Therefore, it's a measure of your signal, how much signal you can detect. It's obvious if we want to go to zero field, we should obtain largest molar polarization. So here we can see experimentally, we found these conditions to be at least some local maximum, and we used this sample to polarize our spins. However, one interesting observation which we did, looking at the results from Professor Duckett, it was clear to us that there might be some interesting field dependence in a region which was not investigated, because usually you polarize protons in using solenoids, and which you can wind yourself, and it's usually relatively hard to build very high magnetic field with the solenoids. They start to hit, and we decided to investigate nonetheless this region a little further, and we indeed found that there is another maximum of proton polarization in SABRE-relay, which was never so far discussed. We cannot explain it completely yet. However, there is a hint that there might be another mechanism which is operative in the same time, more likely with the proposed SABRE-relay mechanism, and that requires further studies. However, we can see that we indeed have relatively large polarization, which we can use for zero field NMR studies. And with the help of postdocs and PhD student James Sales and Roman Picasso-Frutas from Dima Butker's group, we measured indeed zero field NMR spectra of methanol at zero field after polarization performed by SABRE-relay methodology. Basically, after we took the first scan, we already could see indeed the signal after the sample was optimized. We also measured time traces of these signals, because the signals in zero field are less intuitive than in high field. Basically, what you observe is transitions or lines corresponding to different total proton spin. So here is a total nuclear spin of protons is 3/2, here is 1/2. And in our experiments, we observed that they decay almost with the same time. We still don't understand exact reasons why the intensity and line width is different. This will also require further studies, but what's most important, that indeed, despite chemical exchange, SABRE-relay can be used to polarize molecules for their further detection at zero field conditions. And our further goals, obviously, to polarize larger classes of biomolecules, which can be biocompatible. And I wanted to just show my group right now. It's Eric Van Dijk, again, who did most of these optimization experiments. Also, there's a very talented master student, Chin Yan Hook, who will be presented tomorrow. And his work is about visualization of spin dynamics. I think it's very interesting theoretical work, and I also invite you to join. So with this, I would like to thank you for your attention and just finish up with this picture. That's how I try to look at zero field NMR. It's our latest cover from the Journal of Analytical Chemistry with Piotr Put and colleagues from Poland, where a researcher uses tools of ZULF NMR to listen to the music of nuclear spins down at the bottom of frequency range. So I think it's a very, I hope you also find this analogy interesting. And with that, I would like to thank you for your kind attention.
Danila, thank you very much for your beautiful presentation, exciting cover. Very excited to hear about potential new mechanism once you guys solidify your ideas. I see no questions in the question. Actually, there is one question arriving. The question comes from Oleg Sarnikov. What was the maximum polarization you have obtained for methanol in percentage polarization?
So it can be shown from this slide. Basically, this is figure of merit is molar polarization, but you can see that here you have 0.2 molar polarization and the concentration of methanol roughly 300 millimolar. So from here you can calculate your polarization. So you divide these numbers and you have a number in polarization value. So it's not a large polarization, and definitely it can be optimized. Even enhancement obtained by the group of Professor Duckett are much larger. And I'll tell you that maybe it's a mission at this point, but it did nonetheless allowed us to obtain spectra. We didn't degas our samples. We basically just mixed our chemicals and just activated the catalyst and started doing experiments. So definitely there is a room for improvement, as well as for example, Professor Duckett shows, if you deuterate protons in the carrier amine such that polarization is not wasted to this like benzyl group, as it's the case here, you can definitely increase your polarization values. So that's my answer.
Thank you. That's really cool that polarization can be boosted even further. Well, thanks again for the very exciting presentation. I would also like to thank all the speakers in this memorial session for their presentations, for their contribution.